I've copied.
Good. Now can you work out the units and
Yes.
compare with the screen?
Yes, they're matching.
Good. KSP is a solubility product. It is for an ionic solid. Solubility product only apply to slightly soluble ionic compounds because they reach an equilibrium. KSP expression shows the interaction between ions in the solution. Now, more soluble salts, higher KSP, because if it is more soluble, equilibrium will shift to the right. As already discussed, KSP does not contain the reactant. It contains only the product. So it will be shifting to the right. When it is less soluble, lower KSP value. Now you have to copy these 2 points.
Okay. I've copied.
KSP value is only affected by temperature. Concentration is not there mentioned because it is a concentration product. Pressure is not there, the famous factor. But as discussed earlier, pressure is a factor for gases. It's not there. Temperature increases. Normally what happens? KSP value increases. You have to copy these concepts also.
Okay. For the temperature increases, shouldn't it be like, for example, if it's an endothermic reaction, if we increase the temperature, KSP will increase. But if it's in the case of exo, shouldn't the value of KSP decrease?
That's a very good point. That is why I use the word that actually it's a generalization. Normally, we are talking about sparingly soluble salts. In sparingly soluble salts, what happens normally in majority cases, solubility increases when temperature increases. That is why it is written like that. Otherwise, you're perfectly right. Many salts dissolve in water exothermically, and many regular salt dissolve in water endothermically. But this is a category, KSP, for sparingly soluble.
Okay.
That is why we are using a generalization. But like all other generalization in chemistry, there are definitely some exceptions. Now we are putting the title calculations.
Okay.
We are using here 2 types of concentrations from AS chemistry. One is molar concentration and second is gram concentration. And we have a combined formula to convert between them. Gram concentration is molar mass into molarity. You have to copy this.
Okay. I've copied.
Example number 1, at 25-degree temperature, no need to copy the question. I will share inshallah the questions, but data would be needed. At 25-degree, the solubility product, which means KSP, is 4 into 10 power minus 28. Calculate the solubility of lead 2 sulfide. So they have given us KSP.
Yes.
And they have mentioned the temperature. No doubt, temperature is a factor, but temperature has no contribution in calculation.
Yes.
So you can read the question again and make the data, make the equation. Let's make the data, temperature, KSP, name of the salt, equation, and then we want to find the solubility. Here, we want to make a very important concept, which is not a past paper concept, but it's a theoretical important concept, that solubility of a sparingly soluble salt is its concentration of its ions. Even though this doesn't make initially a good sense, because solubility is something different and concentration is something different. But here, because it's a sparingly soluble salt, majority of the salt will not dissolve in water like lead sulfide. So how much lead ions are dissolved, you will find their concentration. And this concentration will be a measure of solubility. So I repeat the concept. Concentration of the aqueous ion of a sparingly soluble salt is a measure of the solubility of the salt.
Okay.
So we can write down this concept and we can proceed with the question also. Concentration of the aqueous ion of a sparingly soluble salt is a measure of solubility of the salt.
I've copied.
So please copy the data. Please copy the data and Then try to solve this equation for concentration. They are in 1:1 ratio.
So wouldn't the solubility also be 4 times 10 to the power of minus 28?
So you can find the solubility either by lead or by sulfur ion, and you can take any one of them. So you have to take, because they're in 1:1 ratio. So when you write down the formula, you can take them equal and you square them. In order to remove the square, you can take under root on both sides and then you can solve it. I think the only difference is coming from the root. Otherwise, you have done it.
Yes.
So compare the working.
Okay, I got it.
Now you can convert it into solubility by this rule. You have found the concentration. Concentration is a measure of solubility. And why you are converting it into gram? This is only a convention that solubility is in gram per dm cube. If you are taking it from concentration, it is not in mole per dm cube. But obviously, that will depend upon the question. And you can leave the answer here, mole per dm cube. But if it is needed, you will first find the molar mass and then convert it into gram concentration. You have to copy this.
Okay. I've copied.
The solubility of ionic compound My at 25 degree is 5 into 10 power minus 10 gram per dm cube. The relative mass, if My is 200, calculate the solubility product of the salt at this temperature. Now you have to copy this. You have read the question, and I hope you have identified that this question is the reverse of the previous question.
Yes.
Gram concentration is always equal to
Molarity
gram
times
concentration is equal to molarity into molar mass. First, you make the data for a so-called impression, and then you have to make a general equation.
So would it be 2.5 times 10 to the power of minus 19?
Have you squared it?
Yes.
Then it's fine. Now our new heading is coming, applications of KSP.
I've copied.
Number one, predicting the precipitate. This is the first application. That what is the benefit of calculating KSP? Now, before starting these applications, there should be a concept to be understood that one KSP is there from the standard table, and one KSP is obtained during the after calculation. It is just like one is a grade boundary and one is the marks you obtain in a paper. Now, there are two KSPs. One is the KSP which is, you can consider, which is the KSP from a table, from the standard values. And one is the KSP which you would calculate from the calculation from the data. If the KSP can be used to predict the precipitate, how? For a spanally soluble salt, we make the KSP and we make these rules. If our KSP is equal to the original KSP, the solution is saturated. If our KSP calculated is less than the table KSP, solution is not saturated. You can still put more salt in water. But if our ionic product, which is our KSP, is exceeding the KSP of the solution from the table value, it means solution is now oversaturated and solution is going to precipitate very soon. So it means what? When we are willing to predict the precipitation, we will calculate our own ionic product, and we will we will calculate our own ionic product, and then we will compare it with the KSP from the table. Is how we calculate it. So after giving the heading, right under it, after giving the heading, right under it that KSP values are available in a table. KSP values are available in a table these values are compared with the value of the ionic product compared with the ionic product to determine the chance of precipitation.
Okay.
Now, copy this equation only.
Okay.
Copy this equation only.
I've copied.
Then then copy this table, this whole screen.
Okay. I've copied.
Now, this is a solve example. Adding a solution of sodium chloride to a saturated solution of silver chloride will result in the precipitation of silver chloride. This is a very interesting ancient chemistry when people used to discover important elements like silver, like gold, and they know that they can be separated from sparingly soluble salt. Silver is also an important element like gold. Silver chloride dissociates in water as follows. Silver chloride decomposed to silver plus chlorine. The solubility product at 25 degree is this. We know the product. Now, what we will do, we will find the ionic product of the reaction. We will determine the ionic product of the reaction, and we will compare it with the value 1.2 times 10 power minus 10. If our value, which we calculate, is equal to this value, it's a saturation point. If our value exceed this number, solution will precipitate. Now, see this example. If equal volume of silver nitrate, this and this, solutions are mixed, will silver chloride be precipitated? Now, you have to see this question. And I will post you the PDF. So the question will be with you. And you can read the question and we can make a data.
It won't be precipitated.
Okay. And first we have silver nitrate solution, we have sodium chloride solution. Silver nitrate and sodium chloride concentration, because we are having, because they are saying the equal volume of silver nitrate and equal volume of silver nitrate and silver chloride are there, but they have the same concentration. Sodium chloride is a soluble salt and silver nitrate is a sparingly soluble. So when you mix them, volume will double. So if you mix them, volume will double, so concentration will be half. Then you make the equation and you have to see the silver chloride precipitate or not. So did you combine them and make the volume half? Oh, sorry, volume double?
Yes.
Good. And if you put them in KSP calculation, the ionic product can be calculated from the data. It's coming this number. And this, our given KSP is this. So the PPT will not form. Compare the R numbers. Are they matching?
Yes.
Okay, good. Important features in KSP calculation, ratio and power both are applied. So when you apply this formula, the ratio and the power functions both are there. So for example, it is a to x and 2a plus and x minus. So when you make the ratio, for example, if x minus is 0.02, the a plus will be 0.04. So when you put them in calculation, you have to double the ratio and also the power. So the two will be acting in two positions. You have to copy this calculation trick.
Okay. I've copied.
Number 2, common ion effect. This is another important application of common ion effect. This concept comes in an idea that when you make a solution and you are getting one particular ion from two sides, it is called the common ion. For example, I make a solution of H2SO4. It will decompose and it will get 2H positive plus SO4 minus 2. Now I also put in the same solution barium sulfate. Barium sulfate is a sparingly soluble salt, but it also releases SO4 minus 2. So from two separate entities, from two separate sources, we are getting a common ion, and that common ion is called SO4 minus 2. Now, from Le-Chatelier principle, if SO4 minus 2 concentration increases, equilibrium has to shift. Sulfuric acid, being an acid, has a so-called equilibrium which cannot be shifted in normal conditions, but barium sulfate is a sparingly soluble salt and the equilibrium can shift there. Now, when sulfuric acid is also donating SO4 minus 2, there is a very high concentration of SO4 minus 2 in the solution. According to Le-Chatelier, in order to balance this, the reaction shifts to the left. The reaction shifts to the left. This will cause more barium sulfate in undissociated form. When barium sulfate increases here, there will be a greater chance that barium sulfate will eventually precipitate. This concept is called common ion effect. So solubility of an ionic compound of a solution is decreased if the solution already contains one of the ions. This is how we put it in the paper, the definition. You have to copy this.
Okay. I've copied.
Right. So we have a solution of silver chloride and we have a solution of sodium chloride and silver chloride. Chlorine is the common ion. So adding a common ion, one which is present in the solution, will result in the precipitation of a sparingly soluble ionic compound. So I'm adding a salt in this solution. This is a soluble salt. But after the addition of this new colorful salt, a salt precipitate out. This is called common ion effect. So we made this one, and now you have to copy this example.
Okay. I've copied.
Now, this is another description point for the concept of common ion. So whenever there is a common ion in a solution and its concentration increases, it can make the sparingly soluble salt more insoluble, which will result in its precipitation. So now you have to copy this.
Okay. I've copied.
So thus one salt has precipitated. Adding a solution of sodium chloride to a saturated solution of silver chloride will result in the precipitation of silver chloride. Why? Because NaCl is giving a huge quantity of chloride ions. Silver chloride is a sparingly soluble salt. It gives chloride ion, but in a very limited number. But after the matching, this is called the common ion. Being a common ion, it can shift the equilibrium in the second reaction to the left. The equilibrium shift to the left. So Ksp will increase and solubility of silver chloride decreases. In that sense, silver chloride will eventually precipitate. So now you have to copy this screen.
Okay. I've copied.
Now, this is the common ion which you have to identify in the paper, and then you have to predict that the ion will reverse the KSP value. You have to copy this.
Yes. I've copied.
So due to the common ion, the equilibrium shifts to the left. So write under it that the equilibrium shift to the left equilibrium shift to the left, and silver chloride can precipitate. Equilibrium shift to the left and silver chloride can precipitate.
Okay.
Now, similarly, calcium sulfate solution is there. The same logic will be applied because we are using saturation of calcium sulfate. So you have to make the same, look for a common ion. When sulfate ions are present and the solution shift to the left, equilibrium will be shifted to the left, and that compound will precipitate. Solubility of silver chloride in dilute HCl is less in pure water because of the common ion, chloride ion from HCl. So if you put silver chloride in HCl, it will dissolve even more less as compared to water. Silver chloride and HCl are giving a common ion. Again, the common ion will shift the equilibrium to the left, resulting in the precipitation of silver chloride.
Yes.
When a slightly soluble solid such as silver iodide is placed in water, an equilibrium is established between the ions in the solid and in solution. In this view, the water molecules that solvate the ions are not shown to simplify the illustration. The solubility equilibrium is expressed by the solubility product. The silver and iodide ions are of equal concentration in the solution. When sodium iodide, a soluble salt, is added, the concentration of iodide ion is greatly increased. This means that the product of the silver and iodide concentrations exceeds the solubility product constant. Because the product of the ion concentrations exceeds KSP, additional solid silver iodide forms until the product of the iodide and silver ion concentrations again equals KSP. At equilibrium, when the product of the silver and iodide concentrations equals KSP, the silver ion concentration is much smaller than the iodide concentration. The addition of sodium iodide, which greatly enlarges the concentration of one of the ions in the solubility equilibrium, has reduced the solubility of silver iodide. This reduction in solubility is an example of the common ion effect. When a slight
addition of a compound with an ion.
This would be a bit long and I will inshallah share it. It's a very good experiment. It's a live experiment, but it will take more time. Selective precipitation. This is our next title. Give the heading, selective precipitation.
Okay. I've given the heading.
Now, I have a solution, magnesium chloride, calcium chloride, and they are mixed together. This is a common exercise. For example, you must have heard about treating the seawater and make it drinkable, or even worse conditions, very dirty water, to make it drinkable. This is a technique which is called selective precipitation. Obviously, all ions in water, all minerals in water are not harmful. Some are very useful, but some are very dangerous. So this is where you want to remove some ions, like here Mg2 plus, calcium 2 plus, barium 2 plus. The concept here is there that you have to convert a soluble salt into less soluble salt. This is called selective precipitation. For example, your solution contains barium chloride. Now, barium chloride is soluble. If somehow you can convert barium chloride into barium sulfate, then barium will leave the solution because barium sulfate is not soluble. So what is the concept? Concept says, if you want to remove a salt from water selectively, you have to convert it into a sparingly soluble salt. For example, in drinking water, if by mistake a salt has been dropped, so now you have to remove it. You can't remove it by simply, because normally water reservoirs are quite big. So we have to treat it by such a salt which can replace the ion and make it insoluble or sparingly soluble. So the heading was selective precipitation. So write under it that this technique is used to remove some particular ions from a solution by converting them into a sparingly soluble salt.
Okay.
So write, for example, and copy this screen.
I've copied.
So we made this discussion. Now we move to our next title. The title is pH scale. This was in our O-level also. Somehow it was in AS, but not as a topic. pH scale is very famous, and pH means power of hydrogen. This scale was originally introduced to tackle the strength of an acid. Some acids are considered to be strong, like H2SO4. Some are considered to be weak, like a bit HCl, etc., like carboxylic acids, ethanoic acid, etc. So pH scale is actually used to show the strength of an acid. Later, this scale was extended for acids, or later it was extended for bases also, alkalis also. So give the heading pH scale.
I've given the heading.
What is the primary definition? It is the power of hydrogen. It is a measure of H plus ions concentration in an aqueous solution. So you have to copy this definition.
I've copied.
Now, the pH is calculated by a formula. pH is equal to minus log of 10 H plus. In such a cases, chemistry has a very good relaxation. Syllabus says, do not go for the chemistry concept. When you have a dominant maths formula, you can answer the question in terms of math. In terms of math, answer means that you can justify your logic from the mathematical result. Like here, you can get a number between 0 and 14, and 7 is the neutral pH. So you can justify if a number is quite low, like 1, 2, it's a strong acid. And if a number is quite high, like 13, 14, it's a strong alkali. Even though strength of an acid and strength of a base are definitely defined in proper terms. But the mathematics, if a proper formula is there, answer can be justified from the formula. So pH is a measure of H plus in an aqueous solution. You have to copy this screen.
Okay.
The first two lines can be left over because they are already copied. The first two lines are copied.
Yes.
Let me know once you have copied it.
I've copied it.
Good. This is the all-time famous pH scale. Why in chemistry logarithm is used? Actually, log has a capacity in maths to remove the power of 10. For understanding purpose, because no detailed working is needed, remember that when the question or paper, the theory says log 10, it is simply LG. Our calculators nowadays can solve all the logarithms, but we need only log with a base 10. It is shortly called LG, which means log with a base 10. Now, if you have a calculator, you can use this interesting understanding concept that what is log 1. You can use your calculator to check what is log 1.
0.
Good. And what is log 10?
1.
Log 100.
It's 2.
So you got the point that logarithm is a real scale converter. So if you take out log 100, it will be 2, and it is so on. So if I have log 1000, it will be 3. Now on a graph paper, if I have to plot 10, 100, and 1000, then I will be totally lost because I can't do that. Can you tell me why I can't do that?
Because the values are too far on the graph.
Because the values are too far. You can't use one scale. Okay, then if I take all of them in logs, if I convert all of them in logs, then I will have to plot 0, 1, 2, 3. Is it easy to plot logically these numbers?
Yes,
So we made a concept, but
it's
is
easy.
the concept? The concept says that logarithm is only a mathematical convenience for plotting a graph, for tackling the numbers. Just like you always hear about the earthquake, may God not, it is there. But earthquake shows numbers in 6.1, 6.2, like that. So when earthquake is there, the numbers are in decimal, but 6.1 to 6.2, the difference is too large. Similarly, actually, all these numbers are either very big or very small. So what we do, 10 power minus 14 becomes 0. 10 power minus 13 becomes 1. 10 power minus 12 becomes 2. This is the advantage of plotting a graph and dealing the numbers for understanding. So pH scale 7 is the neutral pH. It goes on the back side, front side, acid and alkaline. pH values depend on concentration of acid or base and degree of dissociation. Degree of dissociation means when you put an acid in water, it dissociates and it goes into solution. But remember, it is not a crystal, it was already aqueous. So this is called dissociation. So pH of an acid increases upon dilution at constant temperature to a volume V. So pH increase means strength of acid. pH increase means strength of acid decreases. So this is the basic pH scale, and we have the concept here. pH values depend on concentration of acid or base, and it goes reverse. So if you are here, if you reach here on the left side, it is a strong acid. And if you reach here on the right extreme, it is a strong alkali. So strength varies like this. Then we have a formula POH. It is the reversal of that. And we have two formulas. One is the formula in terms of log, and second without log. You have to copy this.
Okay. I've copied.
Right. These are the two formulas. Acids, weak and strong. Weak acids are those which ionizes partially, and strong acids are those which ionizes completely. You have to copy this.
Okay.
It means this table will justify that how suddenly acids enter this game, because the name of the topic was ionic equilibria. Acids are definitely not ionic salts. They are able to dissociate in water, but definitely they are not like salts. They are here because their strength depends upon the degree of ionization.
Yes.
For a strong acid, because it dissociates completely, the strength of the acid is the concentration of H plus. This is a very helpful rule when solving these questions. You have to copy this.
Okay. I've copied.
Good. So we made this concept of a strong acid, and then we will inshallah continue in our next class. Thank you.
Thank you.